A canyon in central Tajikistan is quietly hosting the Rogun Dam, set to become the tallest ever built at around 1,099 feet from foundation to crest. But the visible wall is only half the machine. Beneath it sits a hollowed-out mountain, an underground power hall carved from solid rock, and a river that had to be defeated first. Watch through. Rogun is not what it looks like. Deep inside a canyon in central Tajikistan, a construction site is quietly trying to become the tallest dam ever built. Around 1,099 feet from foundation to crest, the Vaksh River runs straight through it. The obvious problem: the river was there first, and it has no intention of stepping aside for a construction schedule. Zoom out from the canyon floor, and the scale of what is actually happening at Rogun changes the whole conversation. Aerial footage shows a valley that has been reshaped over decades. Terraced roads cut into the mountainside, thousands of dump truck loads a day, drilling rigs, cranes, and a work fleet that runs through the night under floodlights. The plan is not to build Rogun on top of the river. The plan is to build it through the river, around it, and underneath it, all at once. 1,000 feet of man-made mountain does not just rise, it has to be earned, one hard round with the water at a time. And the first round decides whether the site itself can stay dry long enough to build anything at all. And that first round starts with cutting a new path for the Vaksh, because the river does not lose gracefully. Before a single meter of the main dam body could go up, crews had to carve a completely new path for the river through the mountain. The permanent intake structure cuts straight into the rock. Excavators claw at the slope. Drilling rigs punch holes for controlled blasting. Dust and steam rise from the terraces as the mountainside is peeled back layer by layer. Workers dangling on safety harnesses tie miles of rebar into steep concrete walls. Then a shotcrete crew on a cherry picker sprays a wet concrete coat over the mesh to lock the rock face in place. The idea is straightforward on paper. Send the water somewhere it can be controlled, so the dam site itself can go dry. On the ground, it takes years of blasting, hauling, and reinforcing before anyone earns the right to redirect a river. Meanwhile, above ground, the traffic problem alone is worth a documentary. The Rogun site runs a fleet of heavy dump trucks around the clock, moving earth and rock from excavation zones to placement areas kilometers away, day and night, in dust and floodlight glare. Excavators load, trucks haul, bulldozers spread, road rollers compact. A water truck sprays the haul roads constantly, because dry roads on a project this size mean visibility drops to nothing and the whole cycle stops. Every truck that stops moving costs the schedule money, and the schedule at Rogun does not have money to spare. Why does traffic control matter this much? Because on any megadam, the #1 drag on progress is rarely the concrete or the steel. It is the throughput. How much material the site can physically move from point A to point B in a 24-hour period. Rogun runs multiple shifts to keep that number as high as possible. Night shots show the site glowing like a small city, with headlights weaving between drill rigs and loaders in a non-stop loop. Sleep is not part of the schedule. Then, on top of everything else, the site has to run like a functioning open-pit quarry. Aerial views show a canyon floor packed with articulated dump trucks lined up bumper to bumper, waiting their turn at the loading face. Excavators swing steadily. Motor graders smooth the haul roads while trucks are still using them. Drilling rigs on the upper terraces punch new blast holes into fresh rock. Dust rises. Trucks roll. The river has been cornered. The next problem is deciding what to do with the mountain itself, because the space Rogun needs does not exist yet, and it has to be carved out of solid rock before anything else can happen inside it. Once the outer intake takes shape, the harder work moves inside the mountain. 6 massive assembly chambers for the future power units get excavated in parallel, each one a cavern lined with rebar cages taller than a house. Welding sparks fly against the rock walls. A gantry crane inside the tunnel lifts steel components down deep circular shafts that will one day guide water onto turbine blades. Watching a cage lowered into a shaft you cannot see the bottom of? Pick a word for that feeling, because impressive does not quite do it. In tunnels like these, steel rock bolts are drilled into the walls and tested by pulling on them with hydraulic gear up to about 150 kilonewtons, around 33,700 pounds of force, to confirm the rock will hold what gets bolted to it. Behind the traffic, deeper into the mountain, the invisible half of the project keeps growing. Long tunnels lit by floodlights stretch back into the rock. Workers weld rebar cages onto tunnel walls, then pour concrete linings over them to seal the surface against water pressure. Aerial shots reveal what the ground crew sees only in fragments. Dozens of circular shafts, tunnel mouths, and terraces stacked up the mountainside like a layered cake carved out of stone. Cement mixer trucks drive straight through the tunnels to reach interior pores. A conveyor belt system spans a whole side valley, moving processed rock from a crushing plant to a placement zone without a truck involved. Here's the part most viewers do not see. For every worker visible on the surface, there are dozens more inside the mountain right now. Shaft crews, weld cables, and pipe supports. Drilling rigs bore into muddy tunnel floors. A pipe gets pushed into a wall, a cable gets tied to rebar, a concrete slab gets smoothed by hand at the bottom of a hole nobody outside the site will ever look into. All of this. And the mountain has not started keeping the water yet. Once the rock passes its test, engineers do something that still sounds unreasonable. They build a power plant inside the mountain. The Rogun machine hall is not a building perched by the reservoir. It is a cavern carved out of solid rock, deep enough to hold the entire turbine and generator assembly for every power unit, plus the overhead cranes and service galleries above them. Work on the cavern started decades ago under Soviet planning, was abandoned when the project stalled, and had to be picked back up almost from scratch. Rebar cages get built section by section against the cavern walls. Ceiling panels go in overhead. Lighting rigs turn the underground space into something that looks more like a rocket assembly floor than a cave. The whole facility that will actually generate power for 4 countries is buried inside a mountain most viewers will never see the inside of. The machine hall is the reason Rogun works at all. Above ground, the visible part of Rogun finally starts to rise. But this is not one giant concrete pour. The core zone gets built in careful lifts. A boom pump feeds fresh concrete into a dense rebar cage, while workers spread and level each layer by hand. Every pour has to bond cleanly to the one below. Around the concrete core, the rock-fill body of the dam grows outward. Aerial views show terraced excavation pits feeding a non-stop cycle. Drill, blast, load, haul, dump, spread, compact. Rock blasted from the quarry gets sorted by size. Coarse material goes into the outer shells for weight and stability. Finer material goes closer to the core to help seal the structure against water. A wrong stone in a wrong layer, and the dam does not perform the way it was designed to. On a project this large, mixing up your material zones is the kind of expensive lesson you only want to learn once. Now add winter. The Rogun site sits high enough that heavy snow closes in for months at a time. Trucks push through slush on the haul roads, excavators dig into frozen slopes, and the tunnel entrances get blocked by drifts that have to be cleared before the shift can start. Inside the tunnels, work does not stop. Rebar cages go up, welding sparks fly. A drilling rig punches into the tunnel floor, while a concrete trowel smooths a slab 100 meters away. Cold weather slows a construction site. It does not close it. Winter conditions do more than slow trucks. They change what work can happen where. The steep slopes get treated with sprayed shotcrete to lock loose rock in place before spring thaw sends anything sliding. Workers on suspended platforms feed a concrete hose along a mesh-covered rock face, layering the wall like frosting on a very cold cake. Rebar mats get pinned into slopes to hold thin surface concrete in place. Surveyors set up equipment in the snow to check that every terrace is still at the exact grade the drawings say it should be. A wrong reading here means a whole placement layer above it goes in at the wrong elevation, and the correction later costs weeks. Aerial shots show the snow line cutting across half-finished terraces, with drilling rigs still operating above it and shotcrete crews working below. Meanwhile, dump trucks and excavators keep the material cycle running. Fuel lines freeze if the equipment stops, so most of it never does. Some parts of the calendar are named specifically for how hard the crews are supposed to work in them. The 70 Days of Intensive Labor campaign has become a Rogun ritual, a window every year where night shifts run under floodlights, water trucks spray haul roads continuously, and every machine on site pushes toward a specific milestone before conditions change. At night, the site glows. A worker with a lighted signal wand directs traffic between articulated trucks the size of small houses. A motor grader smooths a road while dump trucks are still using it. 3 road rollers work in formation, compacting fresh fill. A tractor tills prepared soil with a disc harrow. 20 years from now, will construction projects in high mountain valleys still run on fleets of diesel trucks? Or will most of this material be moved by electrified conveyor and cable systems instead? Where do you see it heading? Every extra load moved during those 70 days is one fewer load carrying over into next season. Not for show, for math. Watch the aerial view long enough, and the whole site starts to make sense as one continuous machine. Trucks pull out of a quarry face and disappear down a haul road. Excavators cycle non-stop. Tunneling rigs drill into rock faces deep in the mountain. A conveyor belt system quietly moves crushed rock across a whole side valley. No truck, no driver, no fuel, just belts turning. A crusher screens material into the size classes each part of the dam needs. Meanwhile, inside a tunnel, welders work on rebar cages and a concrete truck drives past them without slowing down. The dam rises visibly between winter footage and summer footage. Spillways start taking shape. A view of water flowing through a completed section shows what all of this is finally for. Why does the sequence matter? Because on a dam like Rogun, you cannot rush any one step without paying for it later. The core has to cure before the next lift goes on. The rock has to be graded correctly before it gets placed. The tunnels have to be lined before water touches them. Everything the site produces above ground, the site consumes at the same rate underground. And now, the turquoise reservoir in the aerial shots stops being a promise and starts being a physical fact. Water backs up behind the growing dam body. The valley that used to be a river is becoming a lake. Rows of dump trucks stretch across the flat placement zones, waiting to feed the next lift. Bulldozers push and level. Wheel loaders shuttle material. Rollers pass over and over the same strip until the compaction meter says the layer is done. A crushing plant on the mountainside feeds a conveyor belt that never seems to stop. The finished sections of the dam already hold back a lake the color of glacier melt. The unfinished sections are still eating trucks and rock 24 hours a day. All this man-made mountain has one job left to do: send the water back down, in a way that turns pressure into electricity for 4 countries at once. And the path that water takes from the reservoir to the turbine is a story of its own. Now the water has to actually get to the turbine, and that means steel. Penstock sections at this scale get rolled, welded, sandblasted, and x-rayed in dedicated factories thousands of kilometers away. Every seam is inspected before the pipe ever sees pressure. Then comes the part nobody warns you about: moving a finished turbine to where it will actually spin. A Francis turbine runner for a top-tier hydro plant weighs around 316 tons and stretches almost 30 feet across. That is more mass than 375 average cars stacked in one pile. The delivery convoy uses 3 tractor trucks pulling a trailer with 18 axles per side, riding on 180 tires, and stretching about 330 feet from front to back. Highway lanes get closed, guardrails get removed, traffic islands get bulldozed flat and rebuilt later. Ocean cargo ships carry the load across thousands of miles of open water, then transfer it to river ferries for the final push upstream. Get one bridge clearance wrong by an inch, and the schedule stops for a month. Every part of this trip is planned months in advance. And that is exactly the operation Rogun ran to bring in its own turbine runners. Cargo wrapped in blue protective sheeting, escorted by police vehicles, rolling under archways at dusk, with the Tajikistan flag draped across the front. This is the working turbine runner for Generating Unit 6, arriving after weeks on the road. The convoy moved through city streets at night to avoid daytime traffic, along highways lined with flags, past greenhouses and farms, over bridges spanning the Vaksh, through tunnels cut into the mountain, and finally up the last unpaved switchbacks to the site itself. At the destination, a gantry crane inside the powerhouse lifted the runner off its trailer and set it into position for installation. From factory floor to mountain cavern. One component, one continent, one very patient logistics team. One turbine runner can travel farther on the ground than most people fly in a lifetime. With the turbine in place, attention shifts to the water it will drink from. The Soy Obishur intake dam has been rising at over 900,000 cubic meters of concrete a month, part of a separate structure that manages salinity and sediment before water enters the main penstock system. Because at this scale, even the material handling gets its own dedicated infrastructure. Rendered animations show a full-length overhead conveyor belt system spanning the entire side valley, riding on track ropes and light frames, running from a loading station on one ridge to an offloading station on another. Ground shots show workers fabricating the steel pipe sections that support the belt, welding stiffener rings onto pipes almost 10 feet across. Building the machine that carries the material to build the dam counts as a separate construction project by itself, and it still saves money compared to trucking. With the water routed and the turbines in place, the whole design is finally ready to do what it was built for. The machines that will sit inside that cavern do not get built there. Turbine components for projects this size come from specialist workshops far away. Welded, machined on giant CNC beds, polished, inspected by dial gauges to fractions of a millimeter, and only then packed for transport. Because a generator that big does not just get assembled, it gets grown, one process at a time. Crude steel, around 250 tons per rotor, gets heated to over 3,000 degrees Fahrenheit and forged under 1,000 tons of press pressure. The machined rotor comes out at about 75 tons. The stator uses 144,000 individual steel sheets stacked and bonded together, wound with copper, and tested with oscilloscopes before it ever leaves the factory floor. Every step is measured. Nothing gets shipped on hope. And once all these parts finally sit inside the mountain, what stands above them starts to look different from any angle you approach it. Before generation can happen, one component has to go in. And it does not go in twice. The generator stator, wrapped in protective material and hanging from an overhead crane, gets lowered into its pit at millimeter precision. Would you rather be the crane operator or the engineer signing off on the final position? And this is what the last mile of that delivery looks like anywhere in the world. A turbine runner weighing close to 150 tons hangs from an overhead crane, lowered slowly into the stator ring below. Tolerances at this stage are measured in fractions of a millimeter. The runner has to sit perfectly centered, perfectly level, with clearances that one bad measurement can ruin. Ever tried aligning a 150-ton spinning part inside a hole with less than a coin's thickness of margin, using nothing but crane operators and hand signals? With the cavern hollowed out and the machinery on its way, the site now faces its most visible task: actually raising 1,000 feet of man-made mountain in a canyon that never wanted one there. Here is where all of it, the tunnels, the intake, the penstock, the runner, finally comes together in one continuous machine. Water from the reservoir drops through the penstocks under enormous head pressure, hits the blades of the turbine runner, and spins the shaft that drives the generator directly above it. Aerial shots inside the cavern show the powerhouse gallery lit up. Rows of electrical control panels, thick insulated cables, transformers connected by heavy buswork, and the central turbine assembly with dozens of workers around it. Outside, water gushes from a completed outlet in a controlled release, testing the flow path. Once fully online, Rogun is projected to generate around 17 billion kilowatt hours of electricity a year, enough to power Tajikistan, northern Afghanistan, northern Pakistan, and to export the surplus. The mountain does not care who buys the electricity. Someone will. And the electricity matters more than the numbers suggest. Around 70% of Tajik households face power shortages during winter. Existing dams, like the older Hydroelectric station, built in 1956 with equipment rated for a 30-year life, are being rehabilitated after almost 60 years of service. Rogun is meant to end the shortage. Pull the camera back one more time, and something interesting happens. The turquoise reservoir, the red rock canyon walls, the terraced roads carved into the mountainside. From far enough away, the whole project starts to look less like a construction site and more like part of the landscape itself. But even the landscape shots hide how much of Rogun is imported. Turbine equipment, penstock steel, and generator components come from workshops around the world. Assembled, tested, then shipped by road, sea, and river to a mountain valley in Tajikistan. The most striking example is the T4 transformer, around 390 tons of it, not counting the 8 tons of insulating oil that ships separately. The unit was built in a factory in China, hauled across Kazakhstan on rail, then transferred to a specialized road convoy for the crossing into Tajikistan. The border gate at the crossing had to be widened. Overhead power lines along the route were physically lifted by dedicated crews so the convoy could pass underneath. One weight-limited bridge near the destination had to be replaced with a temporary 10-day bypass because the existing crossing was rated for only 80 tons. At the final approach, the convoy switched to a special self-propelled trailer designed to lower the deck for tight overhead clearances, then raise it again to push through steep grades. 2.5 months of travel for one part. Rogun waits for nobody and delivers to nobody on a normal timeline. On the anniversary of independence, the site tells the same story from a different angle. Drilling rigs punch new holes into cliff faces. Excavators cycle steadily through spoil piles. Welders work inside the powerhouse cavern with sparks flying against dark rock. Blueprints get reviewed on temporary platforms above active work faces. Dump truck cabins pass in continuous convoy. Bulldozers grade the placement zones for the next lift. A group photo of workers in hard hats and safety vests posed in front of the site is a reminder that all of this hardware is run by people. 100,000 workers have contributed to Rogun. That is the population of a small city, all working on one hole in the ground. By midsummer, the site is running at full stride. Aerial shots show the reservoir stretched across the valley in a broad turquoise curve. Excavators and dump trucks work the mountainsides in coordinated cycles. Rollers pass over freshly placed fill until the compaction meter reads what the drawings require. Inside the mountain, welders build up cable trays along tunnel walls. Rebar cages get tied around future concrete pours. A soil testing crew measures moisture and density at the placement face, a step that most viewers never notice, but that decides whether a whole layer passes inspection or gets torn out and replaced. At night, the entire site glows under floodlights. Trucks move under artificial lighting because stopping at sundown is not an option on this schedule. Excavators dig into slopes lit up like a sports field at night. Drilling rigs work through the small hours. Meanwhile, spillway sections are taking shape at the downstream face. The first controlled releases of water are being tested. The reservoir is filling in careful stages, watched by hydrologists and geologists. Every measurement, every load, every welded seam feeds into one number. The day Rogun goes fully online. And here is the payoff nobody expected when they first saw the aerial shots. From the air, the project looks like one giant stone wall in a canyon. But that wall is actually the visible tip of a system reaching deep into the mountain. Tunnels, chambers, penstocks, powerhouse, and generator hall are all knitted together into one machine. The wall, you see, holds the water. The mountain around it holds everything that turns the water into power. The dam is only the surface. The engineering happens underground. Look at what Rogun actually is. A river was cornered. A mountain was hollowed out. A power hall was carved into solid rock deep enough to hold every turbine, generator, and overhead crane the plant will ever need. Turbine parts traveled across 3 countries on trailers with 180 tires. And a wall of man-made rock now rises almost 1,100 feet above a canyon floor to hold back a lake that will power 4 nations. The quiet debate around megadams like Rogun is whether the payoff justifies the disruption. Displaced communities, altered river flows, decades of construction, and geopolitical tensions between upstream and downstream countries. Cheap, clean power on one side, real costs on the other. So here's the question. Should countries with major rivers still build megadams like Rogun today, or should they focus on smaller, less disruptive alternatives? Tell me where you come down. If this made the mountain make sense, hit subscribe. Another one drops soon. See you. Take care.